Hi, I'm Swapna. This is the fourth session of the Feynman path integrals series that I started a few weeks ago. Okay, today I'll be talking about the variational principle. Okay, so this is the chapter 2 of this book, Feynman's path integral with basic calculus. And so what is the variational principle? Okay, so variational principle deals with finding the minimum, of something. Okay, so I'll explain what that something is. Okay, but since it deals with the minimum, then why not start by talking about the minimum of a function. Okay, and how do you understand that the function has reached a minimum at a certain value of x. Okay, so we know from ordinary calculus that if you have a function which has a minimum for a certain value of x, the derivative of the function at that value is equal to 0, right? Okay, let's say this is x equal to x min. So another way to characterize the minimum is to say that the change in the function, which is equal to df dx times dx, is approximately equal to 0, because if df dx is 0, then the change in the function is 0. What that means is if you are near the minimum, then the change in the functional value, let's say this is minimum and you're here, so the function is approximately stays the same, so that happens only at the minimum and at the maximum, at the extrema points basically, right? The change in the functional value is 0 to the first order of the change in the independent variable. Now this is going to be very important for our treatment of the variational calculus. For example, now we are making the transition to the variational calculus. So let's say you have 2 points A and B. The question is, what is the shortest distance between these 2 points? It's a straight line, right? It's very simple. You join them by a straight line, and that's the shortest path between 2 given points. But how do you prove it? Can you prove it? So, what does it mean to prove it? Well, it means that if you consider all possible paths between A and B, like maybe this, and then something arbitrary path. Of all these paths, the straight line, assumes the minimum value. All right. How can you prove that? How can you prove that the straight line has the shortest, shortest length? The way to prove that would be to consider a path which is slightly different from the straight line, which shares the same endpoints but is slightly different from the straight line, like something like this, an arbitrary function. So if the straight line is given by y bar x, then this path would be y equal to y bar x plus eta x. So let's say this is your x-axis and this is your y-axis. All right. So your eta x function, see, y and y bar share the same endpoints, right? So your eta x should be 0 at these 2 endpoints, right? Just to satisfy the boundary conditions. So eta x should look something like, this is this point, and I should be careful. It's kind of like this, So this is eta x, which vanishes at the 2 endpoints. Now it's not a sine, it's not a sine function, it's not a sinusoid or anything. It's very arbitrary. It can be anything. The only criterion is it's pretty close to the straight line. So it doesn't deviate too much from the straight line. If we can show that yx, and the straight line has the same length, up to the first order of variation of eta x, then we can prove that the straight line is, the shortest path. See, it's a similarity with this. So just like here for a function, the change in the functional value, was 0, to the first order variation, in the independent variable. Here, to the first order variation of eta x, the lengths of the 2 curves are the same, up to that order, All right, if that is the case, then we can show that the straight line is the least path, okay? Because the variation is above the straight line, okay? So it wouldn't have been, the length of the straight line wouldn't have been the same with this other curve if, the straight line weren't the shortest path, all right? Do you see the analogy between these two situations? So now, let's actually define certain terms, okay? So as you can imagine, here, although it's similar, it's something slightly different, right? Because here we are dealing with an entire function. So the length is just one number, right? It depends on a function defined over an interval, okay? So length is called a functional, okay? It's not a function. So it's like you feed the length functional, okay, a function, and it spits out a number, okay? So when this happens, like, the input is a function and the output is a number, okay, then this thing, okay, this machine is called a functional. So we can write length as a functional. L, it's sometimes written this way, okay? You can see it's a square, bracket, okay? All right. So in general, functionals are written as functional of any function f of x is kind of written in this using this notation. All right. So okay, so do you see the difference between a functional and a function? For a function, the input is a variable, right? So what is a function? So you have an input variable, it's a number, and the output is another number, right? So it's input, output, okay? Both are numbers, right? But here, the input is a function and the output is a number, okay? For a functional, okay? So the length is a functional, all right? Okay, so how do you calculate the length? What is the formula for the length? Let's get to that now, okay? Length is given by this following formula, integral 1 plus dy dx squared dx, lower limit to upper limit. Okay, where does this come from? Okay, let's say you have an arbitrary curve. Okay, this is a small part of that arbitrary curve, and you can imagine this as you can imagine this thing to be a right triangle, and this ds is approximately equal to, it's approximately a straight line, and this is the hypotenuse of this right triangle, right? So if this side is dx and this is dy, then you can write ds is equal to square root of dx squared plus dy squared, which you can, you can take dx outside, so you can write this as 1 dy over dx squared dx, okay? So then all I did is I took this outside, the square root, and then inside the, inside the square root you have the slope of the line, all right? And then you're integrating this, you're adding up all these small pieces, okay, of the arc lengths of the curve, okay? So this is the formula for the length, okay, of any arbitrary curve, okay? Y is any function, all right? Now, as you can see that, for yx defined over an interval a to b, okay, you get one value of L, okay? So you can see L is a functional, right? Okay. So now let's calculate the length for a straight line first, okay? So let's say that the straight line passes through the origin 0, 0, okay? And it has a slope mx. Okay? It goes from here to A. This is x, this is y. To keep things simple, I let the straight line go through the origin. It will not affect any general conclusion that I draw based on these, specific example. Okay, all right. So how do you calculate the length of this line? Okay, so y equal to mx. So that means dy dx is equal to m, right? So I can write this as 1 plus m squared times a. Do you see that? Like this is a constant, right? And and then integral of dx is just a. So because the limits are from 0 to a now. Okay, it goes from 0 to a. So yeah, it's very straightforward integral, right? There's nothing complicated about it. So this is the length of a straight line that passes through these points. Now let's consider this a small variation about the straight line, right? Remember, like it's this something like this. Okay, so this new curve, this thing is given by what? Y equal to mx is the straight line plus eta x. Okay. Remember, eta is an arbitrary curve, which is kind of, the only constraint on which is that it vanishes at the two endpoints, okay? Of course, it's small, okay, it's a small variation, that's always there, but otherwise it's completely arbitrary, all right? So this is now I'm going to calculate the length of this new curve, okay, which is, which I obtained by a slight perturbation, by creating a slight perturbation about the straight line, okay? All right, so how would I find the length of this curve, okay? So I have to use this formula, and for y, I'm going to use this expression of y, okay? All right, so let's do that. So I'm going to do it here, and I'm going to just draw a line, okay? I'm going to work on the right side, okay? All right, so let's see, y equal to mx plus eta x, right? And I want dy dx, so dy dx is m, ddx of this thing is m, and then you have d eta dx, all right? And I have to calculate 1 plus dy dx squared, okay? Which is 1 plus, I have to square this, and this is like, so let me just write this, square, right? So this is a plus b whole squared, so you have the 1, that thing is there, and you have m squared plus 2ab, which is 2m d eta dx, and then there's another term, which is the square of that, okay? And I'm going to neglect that, okay? Because why? Because it's a second order variation. So just like in Taylor series, we often ignore the higher order terms. Here, we're interested only in the first order variation of eta, okay, for these problems, all right? So I'm going to discard, the second order variation in eta or its derivatives, okay? All right, so I'll just keep the two terms, okay, in this expansion, okay? I mean, these types of approximations are done all the time in physics, okay? So anyway, then I'm going to write it like this, 1 plus m squared, and then you have 2m d eta dx, right? And then I'm going to take 1 plus m squared outside the square root, and I'll be left with 2m, 2m 1 plus m squared d eta dx. Okay, makes sense? Like 1 plus m squared is a constant. I just took it outside, the square root symbol, and this is what I'm left with, which I'm going to expand, okay? Which I'm going to Taylor expand, all right? So this is like 1 plus u, okay? And square root is like half, okay? So I'm going to use this formula. 1 plus u to the half is approximately 1 plus half times u, right? It's a pretty standard, formula, Taylor expansion formula that is used all the time, okay, in physics problems. So if I use this here, what do I get? You have square root of this, and then here you have 1 plus half times that, means m, 1 plus m squared, and d eta dx, right? Half times 2m is just m, okay? And what you have here, this is the final expression, 1 plus m squared, I'm distributing this to the two terms, okay? And then plus, you have m square root of 1 plus m squared, and then d eta dx, okay? Do you see what I did? Like, I'm just distributing this expression to the two terms. This times this is this, and then this times this is going to give you this, and then you have d eta dx, okay? So this is the length, okay, of this arbitrary curve, okay, up to the first order of variation in eta, okay? We just discarded all the second order variations, okay? Now notice something, okay, so I just expanded the integrand, right? So I still have to do the integral, okay? So let's do it here. So I just expanded this part over there, right? So now if you do the integral of this expression, okay, I'm going to do it here. So you have 0 to a, okay, that term. So the first one is I'm going to write it down directly here, okay? You're going to get square root of 1 plus m squared times a, and then you have m squared of 1 plus m squared, and then 0 to a, d eta dx. Okay, so it's actually, sorry, it's kind of looking sort of disorganized. I mean, I'm going from here to here, but it's actually very simple. I'm taking this integrand, and I'm integrating from 0 to a, okay? So the first term is a constant, so integral is going to give just this, and the second term is going to give you this, okay? And what is this equal to? This is the length, okay? So I can call it S curve, okay? This is S curve equal to that whole expression. The first term of which is just the length of the straight line, right? So this is S straight line. Okay? Do you see? So S curve is S straight line, like the length of the straight line. I'm using a different notation here, right? So I was calling the length L, but I'm using S, I'm calling the length as S now. And the reason for this is that, functionals are sometimes, particularly in the context of path integrals, are referred to by the variable S, okay? So, it's called action, but we'll get to that later. So I hope I didn't confuse you by just, coining a different name for the same thing, which is length. Okay, so S curve is the length of the curve, and S straight line is the length of the straight line, okay? All right. So, now I'm going to make a very interesting observation. Note that S curve and S straight line are equal. I mean, you might say, well, there's a second term. Well, look what is happening at the second, with the second term. So you have 0 to a d eta dx, right? This is a total derivative, right? So this is equal to eta a minus eta 0. Okay. Now you remember what eta function is like? It vanishes at the two endpoints, right? This is 0, this is a, right? Remember, this is the straight line. It goes all the way to a, okay? And then you have this arbitrary variation, right? But the point is that, the eta, just the variation part, okay? Not the whole function, but just the variation about the straight line, that vanishes at the two endpoints, right? So this thing is equal to just 0. Okay, eta a equal to 0 and eta 0 equal to 0. So your second term is 0. Okay, so what I showed is S curve is approximately equal to S straight line up to the first order variation of the variable eta. Okay, so this is just like, remember, delta f is approximately equal to 0 when the function, when I consider variations about the minimum of a function, okay? So here, we have this eta x, that's the arbitrary variation about the shortest path, okay? And I found that the functionals are approximately equal, okay? So this is called the stationarity principle, okay? I mean, it's not a hard and fast name, but stationarity condition, it's kind of used, very often, okay, in physics. So I'm calling it as a stationarity principle, okay? So you know that, you have found your shortest path, okay, when you see that the functional, okay, is stationary about this path, which you're thinking as the shortest path, okay? All right. And it's not just true about the length functional. So length is a certain, right? So length has this form, 1 plus dy dx squared dx, right? Now you can have any functional, okay? Not just of this type, but whatever the functional, okay? You know that, you have found a function which minimizes the functional when this criterion, this criterion is met. It means that the functional doesn't change that much, okay? If you vary your optimal solution slightly, only slightly, okay? Up to the first order of variation above the optimal solution, the functional doesn't change. So that's called the stationarity principle, and we will use that principle to find the optimal solutions for different functionals. Okay, we'll encounter different types of functionals in this book. And you'll see that, this stationarity principle is deployed, okay, find the optimal solution, or sometimes it's called a least path. Okay, the optimal solution. So what is a path? Okay, let's clarify that. So path is a function. Okay, right? So as you can see that between 2 points, this is a path. This is also a function, right? Because this is x and this is f of x. Okay, and we use the phrase least path. Okay, to denote that function, that optimal solution for which a functional is minimum. Okay, so that is what is meant by the least path. It doesn't have to do with the shortest length. Okay, when the functional is the length functional, then the least path is the shortest path. Okay, but you'll encounter different functionals. Okay, for which you'll have other types of least paths. Okay, not necessarily the one which has the shortest distance between 2 points. Okay, because this distance is not the right functional there. Okay, you're trying to minimize some functional which is different from the distance functional. All right. Okay. Anyway, so with that, I will conclude today's session, and next time I will show how you derive an equation. Okay, for y by minimizing this functional. Okay, so today we just show that that we know that the straight line is a shortest path. Okay, but what if we don't know that the straight line is the shortest path? Okay, just from this expression, this functional, can we derive an equation, okay, solving which we'll get a straight line? Okay, that is what I'm going to do in the next session. Thank you for watching. Hope you enjoyed this video.